Today's notes is called tweaking parameters. So tweaking means changing. Parameters means just different aspects of the question. So look at your paper right now. What do y'all notice about problems 1 through 5?
They're all exponential.
They're all exponential. They're all curved. They're all increasing. What else? They're all the exact same. Exactly. So what we're going to do is we're going to use this original exponential function, which they've graphed for us. They've given us the recursive rule, which is start and then next equals now times 5. They've also given us the function rule, 3 times 5 raised to the x. So what we're going to do is I'm going to give you a new recursive rule. We're going to graph it, find the function, and then identify how it's different from our original. So the first one, I'm going to change the start value to 5. And I'm going to keep the next equals now times 5 the same. So the original, we started at 3, and then next equals now times 5. So all we did was change the start. Let's do a table of values so we can plot some points. So 0, 1, and 2 is all we have here. So the 0 value, what is that going to be? 5, because that's what we start with. What's the next one going to be? Yeah, because it's times 5, so it's 25. What's the next one going to be? 125, yeah. So let's graph it. So 0, 5 is just above the other one, halfway between 0 and 10. One is at 25, so there's 10. This is 20, and this is 30. So 25 would be halfway between. And then 2 is 125. You can't even fit it on here. But I want to see where it's going to be. So here's 75. So it's going to be all the way up to 125. So let's go ahead and see. If that's 70, then this is going to be 80. Let me extend this line up. 90, 100, 110, 120, 130. So I just added some to my y-axis so I could find it. So this would be 80, 90, 100, 110, 120. So it's 125. It's right there. So let's make the line, which is not a line. What is it? It's a curve. So it's going to start here, curve up, and then curve up. It's going to go on and on. And look at how the other side of this one is. It just goes along the x-axis. It never actually crosses it. So let's just kind of do the same thing. I call it skating along the x-axis because we're never actually going to go below the ice. We're just going to stay above, above the x-axis. So we're going to skate along that x-axis without actually going below it. All right, so how would we write the new function rule? Look at our original, 3 times 5 raised to the x. Following that same format. What? Yep. I'm just going to write y equals. Because we know y equals and f of x equals is the same thing. So y equals 5 times 5 to the x. So what does the first number represent? The start, which is also called what on a graph? Y intercept. There we go. Yep. All right, so what did we have the same on here? Next now. What is that called? The recursive rule, but it's actually called the rate. How it's being multiplied or increased. So let's go ahead and write same rate. What's different?
The start.
Yeah. It's a different start. This will be like a stretch. It's starting a little bit higher, and it's also going to increase faster. So this is called a stretch. It's stretched out vertically. If I were to pull on the end of this, pull it up, that would be a stretch. If I were to push it down, that would be a compression.
What do you mean push it down? Like a downward slope?
Like if I have 2 pieces of wood and I'm pushing down on something, it's going to compress it. It's going to make it flatter.
Yeah.
So this is, see how this one in pencil that I drew, it's a stretch. It's like it's being pulled.
Okay, yeah.
Mm-hmm. All right, let's go to number 2. We have the same thing, but I'm going to change my start this time to 1. So I'm just making these up. And I'm going to keep the same rate. So next equals now times 5. Let's do our XY table. We're going to do the same thing, 0, 1, and 2. Go ahead and fill in your table. So my start is 1, and then I'm multiplying times 5. So 1 times 5 is 5. 5 times 5 is 25. So it's going to start a little bit lower this time. Then 1, 5, and 2, let's say 25. Can I draw this with a straight line? Nope, because it's exponential, it's being multiplied. So go ahead and make your curve. And it's going to keep on going or keep on increasing. And then the other side of the y-axis, see how this is your y-axis? The other side, it's going to do the same thing, just skate along that x-axis. So what's the function rule? Mm-hmm. So 1 is the start, 5 is the rate. And that's how we set up exponentials. That's how we write the equation. It's actually way easier to write exponential than it is our other. Because we know, if we know the start and the rate, well, similar to y equals mx plus b, if we know the start and the rate, we can write that pretty easy. So we can write this really easy by looking at what the start value is times the rate raised to the x power. All right, so what did we keep the same? Rate. next, whatever we're multiplying by. What's different?
Star.
Yeah. The last one was a stretch. This one isn't stretched out. This one's actually compressed. It's kind of pushed down to make it a little bit flatter. So we're going to call this a compression. Even though they have the same rate, because you're multiplying a smaller number. Number 3, we're going to keep the same start, but change our rate. So our start is 3, and our rate is going to be next equals now times 2. How do you think changing the rate's going to change the graph? How much it goes up by? So let's go ahead and do our XY table. So we have 0, 1, and 2. So what's our first value?
3.
And then what's our second?
6.
And then 12. Yeah. Multiply times 2. 3 times 2 is 6. 6 times 2 is 12. So 0, 3, 1, 6, 2, 12. It looks like a straight line, but can I make a straight line with it? Because what's our next number going to be?
24.
24. So it's going to be like that. And the other is going to kind of skate along the bottom. What's our new function rule? 3 times 2 to the x. What was the same about this one? Yep. Same start. What was changed? Yeah. Yep. It was made flatter, so it's a compression. Vertical compression. Number 4. Let's keep our same start. Let's change our rate to 10. So write your recursive rule for changing the rate to 10. So what's our y value? What are the y values going to be? I feel like I've seen those before. Do y'all remember seeing these? Yesterday was bunnies and viruses. The day before was trees. Remember with the acorns? Which would you rather? All right, so let's see. 0, 3, 130, and then I can't even fit 300 on here because that's 70. 140, 28, like it's going to zoom up there. So it's going to go like that. So then this is going to skate along the bottom. What's our new function rule?
3 times 10 x.
Yep. What was the same?
Start.
Yeah. What was different?
Rate.
And how was the graph?
Stretch.
Yep, it was a stretch. All right, the last one. This one I'm going to change both. I'm going to change the rate and the start. All right, so the start's going to be with 8. And the rate is going to be a half. Next equals now times 1 over 2. What's going to happen whenever you take half of something?
So it gets smaller.
It's going to get smaller. So what do you think the graph is going to look like?
Down.
Yeah, it's going to be down. It's going to be decreasing. Let's make our table. So we start with 8. What's the next number?
4.
4. And then
2.
2.
Will this one ever get to 0?
If I keep on taking half of something, do I ever get to 0? No. Do I ever get to a negative number just by halving something? Mm-mm. So it gets closer and closer and closer without ever passing it. Just like the other one. It kept on getting closer and closer and closer, but without touching it or going past it. So it'll never equal 0. So let's graph it. So 0, 8, 1, 4, 2, 2. It looks like a straight line. So what I'm going to do is I'm going to do -1 and -2 on the other side so we can kind of see how it's going to look. How would we find when x is -1? Instead of taking half to get 4, multiply by 2 to go the opposite way. So what would that be? 16. So 16 would be like right there. And then what would the next one be?
32.
Yeah, so you're going the opposite way. So 20, 32. So now does it look more like a curve once we add some more points in there? What's it going to be before that? Before the 32. Be like that. What would be at -3? Yeah. So let's see, 64 would be like right here. It might be a little lower. I don't know. I'm estimating. So there we go. It's almost like a reflection, isn't it? Almost. What's our new function rule?
Y equals 8 times 100.
So this is the same, nothing. So it's different start and rate. Does this have the same rate of increase, like half compared to 5? That'd be like 2 would be the opposite of 1/2. So 5, the opposite of that would be 1/5. Or, the reciprocal. So what caused this to actually be decreasing?
The rate.
The rate.
That's
So rate is smaller than 1. So what happened to the graph?
it would decrease.
Yeah, so it equals decreasing. Would this be more of a stretch or compression?
Stretch.
If it's stretched, it's going up faster, increasing faster. Is it increasing faster or slower?
It's not increasing at all.
Oh yeah, it's decreasing. So it's kind of like a reflection. It's reflected and this is 115 and this is negative 116, negative 2 compared to 275. I'd say it's more of a compression than a stretch. It's pushed down rather than pulled up. It increases or decreases slower. So, and compression. So now answer the question 6, 7, and 8 on your own.
For the entire page. Or
Mhm.
just that question?
The whole page.
Okay.
So which changes resulted in a change in the steepness of the graph? So when we're talking about steepness, we're talking about stretch or compression. But what actually changed that steepness? What was it? The rate. So if it's a big number like 5 or 10, well, 10 is what made it shoot up faster. And then slower steepness would be if it's 2 or 1/2. What resulted in the change of the starting point of the graph? Start value. On the graph, what is that called? Yeah. So we've been dealing with exponential growth. So how does exponential growth compare to linear growth? It's not constant, goes a lot faster. Which one goes a lot faster or slow, or different rate? What'd you say? Curved. So exponential deals with curves, curved. What did a linear have? Straight. I think that'll work. So fold this in half, title it, and put it in your journal. And you don't have homework tonight.